working. Okay. Well, also thanks for inviting me to present in front of you. So this talk is maybe a little bit strange. It's not particularly about Linux, but still I think it's about hardware, hacking, and free software, and what you can do with cheap consumer devices. So I think it will still be interesting to some people. So a little bit of background about myself. I've been working with and using Linux since about '94. I'm doing kernel, bootloader, driver, firmware development for more than 10 years now. But my main focus is actually IT security. So I got involved with NetFilter IP tables, also doing electrical engineering work, and I'm very interested in all kinds of protocols and communication systems, from RFID to GSM. To all kinds of other projects. So I used to be a Linux kernel developer. I'm not doing any kernel development as of now. So yeah, but as I said, it's not about the Linux kernel. It's not about consumer mass market devices. Well, sort of it is, but it's not about how you can sell to a market or something like that. It's about how you can turn a single-purpose device into having many more features than the device had when it was sold. And it's sort of, the idea is to outline the creativity that is unleashed when hardware or chipset makers don't try to lock down devices, and the community comes up and does interesting things. So let me first talk a little bit about software-defined radio. By the way, is anyone in here working for Realtek? No, nobody from Realtek. Well, could have happened. So, if you think of traditional radio receivers, I'm not sure how much people in here know about electrical engineering, analog electronics, and traditional radios, but if you look about traditional, how traditionally radio receivers are being built, it's a hardware-based receiver and demodulator, so you typically have some kind of input filters and analog filters. You have a low noise amplifier, which is an analog active component. You have a mixer, an oscillator, which are analog components, and then you even have a demodulator or something like that built out of analog hardwired electronics. Some of the components may already be digital in more modern receivers, but still it's digital hardwired electronics. It's not software-defined radio. So I want to look at the traditional way how radio receivers are being built. The way how traditional radio receivers are being built in principle, hasn't really changed that much in well, close to 100 years of using radio communications technology. And the new thing, first described in, I think, 1992 in a scientific paper, is a software-defined radio, where you use a more or less classic radio front-end, which consists out of a tuner to down convert from your radio frequency into a baseband signal, or from radio frequency into an intermediate frequency, IF signal. And then you use an analog digital converter to digitize, to quantize the intermediate frequency or your baseband signal, after which you have digital samples, and then you use signal processing algorithms in the digital domain, in the time domain, discrete time domain, to do filtering using FIR filters, IIR filters, and all kinds of components. You can do channel equalization, you can do the actual demodulation of the signal in digital signal processing. Also the decoding, like Viterbi decoder, all these things are done in digital signal processing side in software-defined radio. Now, the reason why, or where do you find software-defined radio, or where are the differences first? Well, having software-defined radio, of course, means more flexibility, because as opposed to hardwired analog electronics or hardwired digital electronics, you have software, and software you can always modify. So you can update, you can improve, you can even implement different communication systems, all just in software. You don't necessarily need to modify your hardware anymore. So as long as some parameters of the system are sufficient, such as the input frequency, the sample rate, and the computing power you have available, as long as those are sufficient, you can, even after the hardware has been designed and years after it has been shipping, you can, just by doing a software update, you can use the same hardware for a completely different radio technology. This is mostly used, the primary users of software-defined radio today is the military. In the US, there's a program called JTRS, JTRS, Joint Tactical Radio System, based on SCA, the Software Communications Architecture, I think is the name. And this is basically building military radios for all kinds of military applications in the US that are software upgradable, and that, so for example, if they do a joint operation with the French army, then they can just download some new software into all their radios and speak the French protocols from the same radio hardware. That's sort of the idea why the US Army is has been investing heavily into software-defined radio. They have put something like, I think, close to $40 billion into research on software-defined radio in the last decade. It's crazy. The other large user or application of commercially for software-defined radio is infrastructure equipment for mobile networks. So all the base stations for UMTS networks, for HSPA, for LTE, they are all large software-defined radios. To give you an example, if you go to Nokia Siemens, if you're a network carrier, an operator, and you go to Nokia Siemens networks and you buy a current base station device, what you get is 17 quad-core DSPs running at gigahertz speeds, plus 2 of the largest FPGAs you can currently buy on the market. That's sort of the computing power that's inside a single base station. It's massive. It's a massive signal processing and computing device for doing software-defined radio. And then you have that hardware, you buy that hardware, and just by uploading different software into the hardware, you can change it from behaving GSM, GPRS, Edge, or UMTS, or even LTE. It's all just different software images. There's no modification in the hardware whatsoever at this point. So this is another really successful and widespread implementation of software-defined radio. But you will notice that, of course, both the military market and the operator market, the carrier market, are very expensive, low-quantity markets. It's not a consumer market. It's not millions of units. And the individual devices are quite expensive. So both the military radio and the commercial carrier base station cost, $20,000, $30,000 each unit. It's not a cheap device. Well, also in consumer electronics, we find software-defined radio. For example, I would suppose everyone's mobile phone that you can find in this room, or can you find anywhere, is using software-defined radio internally in the baseband processor of the mobile phone. So actually, the modern mobile phone chipsets, they are all software-defined radio. However, the problem from my point of view with that is that the flexibility that exists in the hardware is restricted by the chipset makers. So the only software you can run on that baseband processor, especially on the DSP section, is the software that the chipset vendor ever provides you. So while software-defined radio in mobile phones has advantages for the chipset makers like Qualcomm and so on, it doesn't have an advantage for anyone else, because nobody else can modify the code on it. Nobody else is able to just create a different software and install it and make it support new features. So if Qualcomm releases a DSP update for a baseband processor that adds a new feature, okay, then you can use it. But Qualcomm is the only one that can ever provide that software for anyone who runs a Qualcomm chip. So it's fairly limited. The hardware is not documented, it's not intended to be used in a flexible way. The user is locked out of the benefits and locked out of the flexibility that software-defined radio really provides. So it's used even in mass-market consumer devices, but the flexibility is restricted to the original manufacturer. The existing devices that, let's say you're interested in software-defined radio technology, the existing devices that you can buy, well, The military and telco grade software-defined radio, they are very expensive. So for an interested student or some researcher or something, unless you have a large budget, you cannot actually get that equipment. But there are projects like what's called the USRP, the Universal Software Radio Peripheral, which is a device that is intended to be, well, the name says universal. It's a universal radio receiver. You attach it to Ethernet or to USB, and it's used a lot in universities, in education and research, and so on. And there are some even lower cost devices, and I'm going to illustrate a bit more about those devices before we get to the rtl-sdr, which I believe is the cheapest device that you can ever use so far for software-defined radio in a general purpose way. So the USRP is a hardware that has been created by a company called Ethos in the USA. The schematics and the component placement information is public. The Gerber files is not. So it's sort of open hardware, but not entirely open. It's generally available, anyone can buy it, but as I said, it's mostly used in academia, but also individuals can buy it. It's modular, you have a main board and some daughter boards that you plug onto the main board, which implement certain radio frontends. So it's a big step forward in terms of pricing. You don't need to pay tens of $1,000s. It's just a couple of hundred, or a complete system maybe $1,000 to $1,500. But still a fairly expensive price. The system looks like this. So you have the main board on the lower level, and you have plug-in boards that you plug into the main board, which are called daughter boards. And these daughter boards then implement different receivers for different frequency bands. So there's some daughter boards that are maybe for UHF, some other boards for 2.4 gigahertz or 5 gigahertz or any frequency range that you can plug onto it. Block-wise, it looks a little bit like this. You have an FPGA with ADC and DAC, and then you plug in the daughter boards on the left and right. But yeah, as said, still sort of in the $1,000 or more kind of price range, which, well, some people can afford, others, probably don't. So there's some technical specification. I'm skipping over that. It's not really important. Maybe the only important point to note is that the USRP is receive and transmit. It's not just a receiver, it's a receiver and a transmitter. So, and they actually have 4 channels receive and transmit at the same time in this system. They have later done an update called the USRP2, and now there are many other USRPs, different successors of the hardware. Now, the big difference is that most of them use gigabit Ethernet instead of USB, because USB is only half duplex, whereas Ethernet is full duplex. So you can get more data through it. It's very high speed ADCs and DACs, very powerful hardware, but also, again, yeah, it's still in the thousands of dollar range. Now, in 2010, a radio amateur guy in the UK created a device called the FunCube Dongle Pro. Why is it called a FunCube dongle? Because there are some amateur radio satellites that are called FunCubes. And he basically built a receiver that was primarily intended to be used with those amateur radio satellites. And it's a small USB dongle. I'm going to show a picture on the next slide. That supports a very large frequency range from 64 megahertz up to 1,700 megahertz. You can receive any signal in that spectrum. It's very cheap, only lower than $200 for the device. And the big problem I perceive with it is that the bandwidth is very small. It only supports 96 kilohertz wide signals, which, well, is for amateur radio purpose may be sufficient, but for any other commercial or other communication technology, the bandwidth is too small. The reason why they chose 96 kilohertz is because actually it appears as an audio device. You plug this radio receiver into your USB port, and it enumerates as a USB audio device with a single sample frequency supported 96 kilohertz, and your left channel is the I samples and your right channel is the Q samples. So without any host driver or without any specific application, you can just read samples from your audio device, but it's not audio samples you're reading, it's baseband samples, I and Q baseband samples from your radio signal that you're reading. So I think it's a very interesting hack that way. So for some systems like Tetra or amateur radio, you can use it, but most other communication systems, it's too narrow band. But I think it's a great progress. You know, we're coming from $10,000 to $1,000 to $200 now for a software-defined radio receiver. If you look at the device, it looks like this. So you can see this, the USB plug is here, and then you have a codec chip, and the codec chip is here. It's a chip tuner over here, and this is a microcontroller on which they run the USB stack. And you have an SMA connector on the other side to connect the antenna. It's already very small, you can see from the scale, but as I said, unfortunately very limited. Now there's another project, and that project actually I'm heavily involved in, is called Osmo SDR, which is sort of in the same price range, about $200 US, but has much larger bandwidth, 1.2 megahertz compared to the 96 kilohertz. It's also a slightly larger device, and it's completely open, so schematics, software, FPGA, bitstream, everything's available. Well, now I'm going to do a quick detour to also introduce GNU Radio to you, which is, of course, we have heard, well, there are many different hardware devices, and there's also now the Realtek devices that you can use for software-defined radio, but what kind of software am I going to use it after I have the hardware? And GNU Radio is a project, it's a free software project, like Linux, like many others, which implements software-defined radio for many, many different communication systems, and it is very powerful. And the idea, or the philosophy of GNU Radio is to not implement software-defined radio as a special purpose, handcrafted, assembly-optimized code for a specific DSP chip that nobody can buy, or unless you're building a product and building tens of thousands of units or hundreds of thousands of units with it, but to do all the software-defined radio signal processing on regular PC code. So GNU Radio is C++ code with some low-level assembly optimizations, but generally it's C++ code. You can compile it on ARM, on PowerPC, even supports the cell processor in PlayStation 3. It's a source code you can compile on many different platforms, including Windows, Mac OS, and so on. And since the modern PCs are so fast, you have many cores, high-speed cores, it's possible to do all the signal processing even on a regular CPU that's not a DSP. And it implements individual signal processing blocks in C++, and you glue those blocks together by using Python scripts. So let's say you have an FIR filter block and an audio output block, and you can connect those different blocks with a Python script. So you don't have to actually write C++ code and compile it, but you can use from Python and connect those blocks in what's called a flow graph. And you can think of the flow graph as plumbing together all the different blocks that pass data between each other. I think this is an example flow graph for a wideband FM receiver, and it even has a graphical user interface where you can click and drop and make these connections of the blocks. So you don't even have to write Python. So here we have an Osmo SDR source which represents our samples coming into the system. We go into a low-pass filter, and the low-pass filter has certain parameters that you can configure. And from the low-pass filter, we go into a already provided block for wideband FM receive, and from that we go into an audio sync, and the audio sync is our sound card, so we can actually listen to FM radio. So when you want to build an FM radio receiver, all you need is some SDR hardware plus GNU Radio, and you need to click together these individual components, and then you can experiment, putting different filter parameters and so on to work with it. There are also some graphical syncs like FFT sync that can show you the FFT of your spectrum or something like that. So you can just add all these different components and create a receiver applications graphically. So this is a more complex example for a single sideband receiver. Single sideband is a modulation scheme used in amateur radio, and you can create very complex flow graphs this way using Blue Radio. Sinks and sources and so on. I'm just going to skip through that quickly and get to the actual Realtek part of it. So there's a Realtek component called rtl-2833U, and it's used in a very cheap consumer electronics DVB-T receivers. DVB-T, I think, is also used in Taiwan, right? For digital television, terrestrial television, so I don't need to explain what that is. So it's basically one of these cheap, small USB DVB-T sticks that you can buy probably everywhere around the corner. In Europe and the US, they sell typically for something around $20 US. So we come from 10,000, we go to $1,000 to $200, now we're at $20. However, of course, the way how they are sold is as a DVB receiver. And they are a classic hardware DVB-T receiver. So in the normal mode of operation, they include a DVB receiver hardware block inside the RTL chip. And only the demodulated and decoded MPEG-2 transport stream is sent over USB into your whatever video application you may use on your PC. So it's not a software-defined radio receiver. Realtek actually released a GPL licensed Linux kernel driver for the device, which many people found very nice of them. It's not mainline coding style and so on, but it's at least GPL licensed free software driver for Linux. And it also, Realtek released a limited datasheet, limited programming manual to the Video for Linux developers, so they could improve that driver and work on it. But still, it's only for DVB reception and nothing else. The device looks like this. So a typical device is an EasyTV668. You have a USB plug. This is the RTL chip, the Realtek chip. And this is a chip tuner, and you connect it to an antenna socket, and that's it. It's basically a device. I mean, they still have a crystal here, and this is an infrared receiver for your remote control, but basically it's the RTL chip plus a chip tuner. And that's your entire receiver design. This is another one, even smaller design, where again you see the RTL chip, and this is an Elonix chip tuner, and this is an MCX connection for the antenna. There are more than 20 different devices from various vendors that we have found which use this chip from all kinds of brands, Teratech, Gigabyte, all kinds of brand names. And they're all based on the same reference design. The only major difference you can find is the mechanical size and which silicon tuner they use. There's like 6 different silicon tuner chips that are used. The best tuner we know and we have found is the Elonix E4000, which you've also been seeing on that picture, is it covers the widest frequency range. All others have much more limited frequency range. Now, how can we use this as a software-defined radio? Well, there are certain vendors who provided Windows drivers for this chip that not only were able to receive DVB, but who could also receive FM radio and DAB radio with the same chip. So then some developers thought, how do they do this? It's a DVB receiver and hardware. How can you turn it into an FM receiver or do a DAB receiver with it? And the Linux driver had no FM radio or DAB support that Realtek provided. The data sheet did not indicate anything about hardware blocks for FM radio reception or anything like that. And people were sniffing the USB protocol between the USB device and the Windows driver and discovered that, well, it's forwarding raw baseband samples from the chip tuner basically to the ADC, and then forwarding the raw samples into the PC, and the Windows driver in software on the PC is then doing the FM radio demodulation or the DAB demodulation in the x86 software. Realtek didn't provide documentation or source code for this, not even upon request, even though they have Linux drivers and they have provided documentation on the normal TV operation. But by analyzing these USB traces and reverse engineering, it was possible to write a new driver, and that's what we call rtl-sdr, which is based on libUSB, so it's even user space only. You don't need to put anything into the Linux kernel for that. And where we trigger this raw sample transmission by the Realtek device, get the raw samples into the PC, and then interface that with GNU Radio or many other software components to implement that. Funnily, some of these Realtek devices use the same chip tuner as we use in the Osmo SDR project, the hardware that I'm involved in. So we could reuse that E4000 driver that I had written together with the reverse engineered USB protocol to build this rtl-sdr software, and now we can tune to arbitrary frequencies between 64 megahertz and about 2 gigahertz. And I think it's about 4.2 megasamples sample rate, so complex sampled 4.2 megahertz samples. So very wide band, very flexible, wide frequency range. And there's a number of components now, librtl-sdr, rtl-sdr, command line tool, a GNU radio source block, and so on. There's a homepage about the project. Even there are pre-built Windows binaries for users who are not software developers but who are more into radio and electrical engineering. They can because it uses libUSB, it's portable, it runs on all operating systems. And there are many different, now in a very short time, within something like 3 months, a lot of different software projects have added support for this rtl-sdr. People have been writing all kinds of decoders and porting decoders to this interface, so you can now use that $20 US device and free software to demodulate AM radio, FM radio, wideband FM radio, single sideband amateur radio, DAB. You can receive GSM downlink from the base stations. You can receive Tetra, like on airports or police radio and so on. You can receive Thuraya satellite radio. It's called GMR. It's the satellite-based telephones where you can receive the signals and decode them, put them in Wireshark. You look at the protocol traces. P25 is the public mobile radio system used in the US and in Australia for police and emergency services. There are RFID receivers that you can use with it. You can use it for digital European cordless telephony, for DECT, and that's just what's happening so far. And I think it's amazing what you can do with something that costs $20 US and which is only intended for stupid TV reception. And you can turn it into something that's much more powerful, where you can receive many more signals, only based on free software. So. And the only way this was possible is because there's some debug mode in the chip which sort of disables the internal DVB-T decoder and demodulator and forwards the raw samples over USB into the host PCs. I think it's not even an intended feature or something that is maybe not even part of the product specification at Realtek, but by just exploiting this mode and sending the samples over USB, it's possible to implement all those kind of things. And personally, I feel very, very happy about this project because it shows to me the true value of what a hack is in its true sense. Hacking is not breaking into systems, but hacking is creatively using things in a way they have not been designed to be used and turn them into something that's more than they originally have been. So I like that very much, even though my involvement is very, very small in this project, and but still it's a very, very interesting project to see. So who needs all of that? Well, of course, you can receive all kinds of radio, fine, but there are students who want to learn about signal processing and who cannot afford a $1,500 USRP or something like that, but everyone can afford a $20 USB dongle. There's no reason why any student interested in software-defined radio cannot afford such a device. If they have a computer for, I don't know how many hundreds of dollars or thousands of dollars, they can surely afford a $20 USB dongle. So they can do all kinds of research and study on that. Radio amateurs, of course, communications researchers, well, anyone interested in building software radio receivers. So of course, like from a commercial point of view, for companies like Realtek, it's of course not a market that really matters, because, well, the number of people who want to watch TV and who don't care anything about technology it's definitely much larger than the market of people who want to play with software-defined radio. That's for sure. But well, you can say the same is true for Linux. You know, most people just use Windows on their PCs. They don't care about all this technology and whether it's free software or not. But I think we have some analogy here that it's a small niche market, but the niche may be growing, and more things can be done with the same hardware by using this. Now, I have a couple of screenshots here. This is an FFT plot for multiple carriers of Tetra. So these signals you can see here are 25 kilohertz wide Tetra carriers. This is Tetra is if you're not familiar with it, is used worldwide by lots of professional mobile radio systems at airports, police, firefighters, even train operating companies are using Tetra. I think the Coast Guard of Taiwan is also using Tetra. This is this frequency plot of the Thuraya satellite phone system, where we have, as I said, we also have a receiver and decoder for that system. People have even done GPS reception with software implemented GPS receiver on the Realtek SDR. It's possible. It's performance may not be as good as a dedicated hardware GPS receiver, but it's possible to receive and decode GPS using that. This is an Inmarsat spectrum plot here from Inmarsat maritime and data radio system. Waterfall plot up here. And yeah, this is basically what I wanted to demonstrate to you, or show to you, what this project is and what people can do with it. So if any of you have an interest in software radio or digital signal processing, I would recommend to buy one of these $20 devices. And I assure you, if you are fascinated by this topic, you will never use the device to watch TV again. Okay, well, I'd like to thank Steve Markgraf and Dmitry Stolnikov and Sylvain Mounant. These are the three main guys writing the code for rtl-sdr. And of course, also thanks to Realtek for at least providing the TV-related source code and for releasing a GPL licensed driver in the first place. If they hadn't done that, it would have been much harder. Okay, well, thanks for your attention, and if you have questions, feel free to ask.
Well, although the Realtek device is very cheap, but it can only receive, right?
Yes.
Yeah, it cannot transmit. So do you have any new target to hack in, which are both way?
Okay, regarding both way, well, this system, the Osmo SDR, which the hardware that I'm involved in building, is a pure receiver, and later this year, we will also build a stacking board for a transmitter. Of course, it will not be a $20 device, right? But since it's low quantity in a niche market, but it's open hardware, schematics are there, the firmware, FPGA bits, everything is in source code. So I think it will be still the lowest cost option so far for also having a transmitter, a universal transmitter. Right now, if you want to do anything that transmits, I think the cheapest options you have are the USRP devices, and they're again in a 4-digit US dollar kind of range, and not in a 3-digit range. So we hope with Osmo SDR we can at least bring it into a 3-digit range. Yeah, I'm not aware of any devices that can transmit that you can use as SDR. Theoretically, it would be possible using any cell phone, theoretically, right? Because if you look at all the UMTS chipsets, UMTS signals are 5 megahertz wide, very wideband, that's why it's called WCDMA. You have high sample rates, you have very good amplifiers because all the QAM16 and the higher modulation schemes need very good quality receivers and transmitters. But the problem is, of course, that none of the bits that relate to the DSP part, not even the DSP instruction set in the Qualcomm devices is known. So they have a proprietary DSP architecture with their own proprietary instruction set, surrounded by proprietary peripherals, and none of this information is even disclosed to the cell phone manufacturers, because the cell phone manufacturers, well, they care about the ARM, they care about the electrical integration, but no cell phone manufacturer ever modifies or you know, changes anything in the DSP part of the baseband chipset. But theoretically, any cell phone has the capability of becoming a universal software radio. But yeah, it's the industry that prevents that from happening so far. Yeah.
I remember people were playing with Morse code on Linux 10 tens of years ago. Do people play with Morse code on the GNU in the radio?
With Morse code, I mean, you could do it, but I don't think Morse code is much in use anymore these days.
It's more fun.
Yeah, well, of course you can do it. I mean, writing a software radio receiver or transmitter for Morse code is probably the simplest thing you can do, because you just need to switch it on and off. It's just on-off keying basically, but you don't need any kind of you know, PSK, ASK, FSK, any of them really, the modulation or even the complex modulation. It's very, very simple. So I think you don't even need to know anything about software, but you don't even need to know anything about DSP, digital signal processing, and all the math. You don't need to know anything just to have Morse code. It's by using GNU Radio, you know, and just the graphical user interface, without writing any Python code, without ever writing a line of code, you're probably able to just have a local oscillator of whatever, how many kilohertz, and then you have a switch, and then you upconvert it. I mean, you send it to your device and send it, or receiving it is also very simple, because either there is a signal or there's not a signal, and you can of course recover that whether there's, you know, the Morse code is transmitted at the moment or not. So I think that's very simple to do. But I'm not aware of anyone having done it. It's probably too simple. I think the most simple things that I've seen with GNU Radio that people do is the old analog radio, like AM radio, FM radio, shortwave, AM radio, single sideband radio, that kind of stuff. But yeah, there's no reason why you cannot do Morse code.
Okay. 好，那没问题的话，那我们谢谢这个卡罗。那我们